All right, and go ahead and open. Go ahead and open the document up. Now, for those of you that came from second block, you've already noticed it's already a little louder.
Other Sydney.
It's other Sydney, yeah. But keep in mind that this is usually the block I record, the lecture. So your voice, may be on. It'd be on YouTube. That's right. You gotta be careful, as I've found out. You have to be careful what I'm talking about. But anyway, because Riley is gone, so we'll record today. But all right, so we're going to work on this idea of a slope field. So if you would go to the second page on your document here, and just read through that. Read through that screen. Read it over a couple of times. All right, so before we move on to the next page, says slope fields provide a graphical method to find a particular solution to a differential equation. The particular solution depends on the initial condition. So, again, let's shake the rust off here a little bit from quite a bit ago. Back in Chapter 2, we did this work with differential equations. We did some work with it in Chapter 3 as well, as we were learning some of those derivative rules, but mostly in Chapter 2, so it's been a while. Two questions that I always ask you about differential equations. One was, what is a differential equation? What was the answer to that? What is a differential equation? It was very simple. That was all it was, an equation that involved derivatives. If it's got an equal sign, and it's got a y prime in it, now this one has dy dx, but that's the same as y prime, right? Matter of fact, I'll probably try to start using this notation more often. As we get into Chapter 4, it's going to be very important to understand that notation, and that just means a derivative of y with respect to x, which is the same thing y prime means. It's slope, it's derivative, but you'll see dy dx a lot, but it's the same as y prime, okay, same thing. So if it's got an equal sign in it, and it's got a y prime in it, it's a differential equation. I mean, it's that simple, okay? And then the second question I always ask was, what is a solution to a differential equation? What's the solution to a differential equation? The original equation, right? Now, we had three different types of differential equations that we talked about. Okay, one was this first type up here, which, what was the key thing about this first type of differential equation? What was different about this compared to this compared to this? We can solve it. And what is it about it that tells us we can solve it? It just has x or t, the input variable, in there. So the solution to the differential equation, if I made a column over here for the solution, what would be the solution of this equation here? Since it has y prime, the solution would be what? Y, but I mean, it would be y equals, right? The original function. So if it's y prime, if this was p prime, the solution would be p equals, right? Or if this was, something else prime, it'd be that. Okay, so it's y prime equals 3x, and the solution is y equals, and then in this particular one, we could solve it, right? What is it? Plus some constant c. And that was, we called that the general solution of this differential equation. But the specific, or what your document here calls the particular solution, would then depend on some initial condition. Remember, we called that an IVP, or an initial value problem. An initial value problem was a differential equation plus an initial condition. So if I gave you this differential equation and told you one point on the y graph, then we could figure out what c was. And we would find our particular solution. Okay, so that would be the solution to that. So we know how to solve those, so that's easy. Okay, what about this one? Yeah, we memorized that solution. That was y equals ae to the kt. It didn't have anything to do with an antiderivative. We didn't know how that solution came about. We just know that's what it is. We just memorized that. Now tomorrow we're going to add another one to this list of memorized solutions, okay? And then we have this one here, like the one that we're going to work with in this calculator document. What was the thing about the third type of differential equation? We don't know how to solve it. It's a mixture of x and y's. We're not going to memorize those solutions. You can solve them. It's just we don't know how yet, right? We don't know how to solve this one, but it could be solved, possibly. Okay. So we don't know. We don't know what the solution is. So that's where slope fields come in. Slope fields are a graphical way to find, or at least to approximate, a solution to a differential equation. It's a graphical solution, not a equation solution. It's not the original function y as an equation, but it's the graph of the original function y. Okay? That's what a slope field is. A graphical solution to a differential equation. And of course we should know that the solution to a differential equation is the original function. So a slope field is a graph of the original function. Slope field is a graph of the original function for this particular one. So we have our differential equation here, the slope field, and that's where we go on to the next page then on your calculator. This is a picture of a slope field. Just ignore the blue graph for a second. Just pretend the blue graph isn't even there. And this series of segments makes up a slope field. Okay? Well, what's that mean? Well, it means that each of these little segments is showing that the direction of the y graph, if it went through that point. If the y graph went right through here, it would be kind of going about in this direction. If it was going over here, it would be going kind of in this direction and so forth. Those little segments are showing the slope of the y value. Where do you suppose the slope came from? The differential equation, because the differential equation gives you slope. It's y prime. It's slope. Okay. So if I was to plug, say the point, let's take the point 2, 2, for example. Plug a 2 in here for x and plug a 2 in here for y. Tell me what you get. Plug a 2 in for x and a 2 in for y. Just do that in your head real quick. What do you get? 4. So that says at the point 2, 2, y has a slope of 4. The y graph will have a slope of 4, right? Isn't that what that's saying? Y prime is a slope of the y graph, and I put a 2 in for x and 2 in for y. That would be a point on the y graph because it's x and y. This is the y graph that I'm looking at right here. So at 2, 2, right about in here, the y graph will have a slope of 4. Now, does that segment look like it could reasonably be a slope of 4? Yeah, pretty steep, right? Over 1 up 4. So that's what those little slope segments represent. One of the things you will do, actually there's 2 things I want you to do with slope fields. One is to be able to draw a slope field. That's something we'll get to later. Well, that's how you draw it. You just start picking points. It's almost like plotting points back in algebra class. You start picking points for x and y, plug them in, figure out what the slope is, and you draw your little, instead of plotting a point, you draw a little slope segment that has that particular slope. And you get enough of those and you kind of see the shape of the graph. All right, so what's the blue curve? Well, the blue curve would be for this initial condition. So here we have an initial condition of 0, 1. So that's the red dot. And then from that initial condition, we just kind of go with the flow. You start here, you can see that the slope segments kind of are horizontal, so it's kind of horizontal, then they start to bend up, and then they start to bend up more, and then here they get flat again. Coming back this way, they look like they kind of bend down a little bit, bend down a little more, and then they get flat again. Okay, now you're supposed to, on question number 1, on your worksheet here, you're supposed to grab that initial condition, move it around, see what happens. Okay, go ahead and do that. Yes,
So you find the slope field first and then you do it.
that's right.
You don't use the condition and then.
Right, the slope field comes first, right, in finding the solution. Matter of fact, we're going to look at some slope fields where we don't even have an initial condition. We'll just look at the slope field. Now, some people in the art class said theirs was kind of slow reacting, but then others weren't so bad. Okay, just to answer that first question on the worksheet then. Okay, go ahead and go to the next page, and the next page on your calculator and then that's the second question on your worksheet. So go ahead and do that. And you can talk with a partner if you want to or whatever, but the second question on the worksheet, go ahead and do that. Okay, so have you got those? I mean, it doesn't take very long if you know what to do, right? What are you doing to answer the question 2? Somebody quickly. Just plug it in, right? Well, are you looking at the point here, or are you going to this? Okay, but we should do the one that's the most accurate. I mean, isn't this is the differential equation, right? So when it asks for the slope, what's the first one it asks for? -1, -1? So if we want the slope at -1, -1, isn't that just saying to do what I just did a minute ago when I plugged in a 2 and a 2? So aren't you just plugging a -1 in here for x and a -1 in for y? Okay, that's what we should be doing. That's what we should be doing. Okay? That's what a differential equation represents, right? A differential equation is y prime. It's telling you the slope of y. And so if I want to know the slope at the point -1, -1, that's when x is -1 and when y is -1. And so that's what we should be doing. Okay, what do you get? Anybody get something there? -2. Now, for along with what Steve said, if I go here to the point -1, -1, which would be about right here, does it look reasonable that the slope is about -2? I mean, looking at these slope segments, right? It looks like it is. Now, I can actually manipulate my graph, change my initial condition to make the graph go down through that point. I could actually put the red point there at -1, -1, and does that look like it has a slope of about -2? Looks like it does. Okay, remember, this blue graph is the y graph. This blue graph is the solution to this differential equation. And every time I change with a new initial condition, I get a different solution. But that makes sense. Just like here, every time we add a different initial condition, we get a different c value, we get a different solution. Okay, a different y graph. All right, what was the next one? 0, -3. What'd you get for a slope there? 0. 0, -3 is down here. And sure enough, it looks like it would have a slope of about 0 there, right? Okay, next one, at 1, 1. At 1, 1, it looks like it's got a slope of 1. If I would drag so that my point goes through 1, 1, sure enough, that looks pretty reasonable that that would have a slope of about 1 right there. And for the last one, -2. So over here at 1, -1, looks like it has a slope of -2. Looks about right. And notice, though, how the blue graph changes depending on where the initial condition is. Now, this is quite a bit more complex of a differential equation than our simple one here. And so the graph, the y graph, is kind of a unique and strange-looking thing. Okay? And when you change the initial condition, it really changes a lot. For example, when you move that initial condition above the x-axis, you get that kind of horizontal asymptote going on. When you're down here, it's more of a vertical asymptote kind of thing, and the horizontal over here. Okay? What if I just gave you this? Let's move ahead a page here. Or maybe you're already on this page. Let's see. Excuse me. All right. What if we were just looking at this? Here's our differential equation, and I just ask you, where is the y, where is the solution going to have a slope of 0? Just looking at this, where are we going to have a slope of 0? When? When x is 0. In other words, I'm asking you, when does this equation equal 0? Right? Well, when x is 0, it's already factored, so that's one place. Okay, we already saw that. Let's go back to the graph. When x is 0, which would be right here, it looks like, along the y-axis, it looks like the slope was 0 every time, wasn't it? Okay, so anytime x is 0, we're going to get a slope of 0. Okay, what else? 3y minus y squared, anytime that is 0, right? Which would be when? 3 or 0, right? Because you could factor out a y, right? So anytime y is 0 or y is 3, let's take a look at that. When y is 0 is along here. Well, yeah, looks like it's horizontal. That didn't get to out here, but I don't think the graph will ever go through there. When we got to this, we had a vertical asymptote over here. Okay, so when y is 0 or when y is 3 up here, sure enough, up here when y is 3, it looks like we have a slope of 0. All right? So I'm going to send this to you, and I'm not going to send it to you. I'll just let you do it. All right, next, go to the next page. Go to 2.1 on your document. I think this is question 3 on your worksheet. So you can answer it on your worksheet or on the document, on the calculator, doesn't matter. Okay, read that and answer that one. Actually, if you do it on your calculator, you can actually check your answer. Once you click in the box and make your selection, you can go to menu and you can check your answer. See if you got that. Okay, what'd you get? -1, right? The slope will be 0 when x is -1. Go over here to the menu, check our answer. Yay, we got it right. Okay. All right, now look at the back of your worksheet for a second. Everybody turn to the back of the worksheet. And this goes to something that Natalia asked a little bit ago. All right. Here's something that you're going to be doing here in a little bit. You're going to be matching, and this is the second thing that you're going to have to do with slope fields. One is draw a slope field. Another is be able to match the slope field with a differential equation. So you've got a bunch of different slope fields, and notice there's no graphs drawn in them. There's no blue graph drawn in. This is a picture. The slope field is a picture of the y graph, or y graphs, I should say, because there'd be an infinite number of them, right, depending on your initial condition. When you look at A, my hope would be that you don't just see a whole bunch of wavy lines all over the place, that you actually could look at A and envision a y graph that is what kind of shape? Don't you see a sine graph kind of in there? And it looks to me like it would be just some sine graphs. So it would be, and when I say, just kind of go with the flow of the shape of those curves. Okay, they kind of come down like this, and it seems to kind of level, and then it seems to kind of go up. And I just kind of follow the curve of those segments. Okay? And where did those little segments come from? They come from the differential equation. They're just little pieces of slope. You just do what we just got done doing. You have the differential equation, you plug your points in, you get a slope, you draw a little segment that has that slope, and you repeat it. And you keep repeating it over and over. Now, I'm not going to make you draw ones that have that many of them, that you'd have to plot. That would take a long time. Okay? But we'll have a number of them to do. Okay? But once you have the slope field, you can just kind of see then in the flow of it, with the slope, what the y graph might look like. Now, we don't know where it would be up and down or whatever because of the initial condition thing. Okay? So you've got that. Now, look at C here. What kind of graph do you envision in there? A vertical asymptote? I mean, I see what you mean by it going down, but I think it looks more like an exponential where it really wouldn't be a vertical asymptote. It would really kind of keep going back this way. It's kind of a flipped exponential kind of thing. If your initial condition was up here somewhere. It looks like it kind of has levels to a horizontal asymptote. Right? See, that's what I would see in there. I would see kind of an exponential graph in there. How about this one? How about E down here? kind of a cubic. I mean, it's kind of steep back here, and then as it comes up, it kind of levels, and then it seems to level like so, and then it kind of goes, heads back the other way. Kind of a cubic kind of a look to it, all right? So, and that is another thing. I draw a slope field matches slope field with a differential equation. And then another thing I'll want to do is if I give you a slope field and then give you an initial condition, I want you to be able to plot that point and then kind of sketch in what the curve would look like. But see, it's still an approximation because when I have my initial condition and then I just kind of go with the flow, that's not very exact. I mean, I don't know exactly where those points are going through, but I can get a pretty good idea. I can get it fairly close. All right, so now the next question that we're going to talk about is going to be this. How can I match a slope field with its correct differential equation? How can I match a correct slope field with its differential equation? Would it be easier to just look at this equation here and then find the slope field that goes with it? Or would it be easier to look at the slope fields first? I typically look at the slope field and then kind of try to narrow it down kind of by process of elimination. Let's look at B here. Just by looking at slope field B, what information could you get about the differential equations over in the left-hand column? Okay, one thing that you might notice is it kind of looks parabolic, right? Which would mean what? So would that be like number 1 then? I agree with what you said about x squared. I disagree on what you said about it being number 1. Well, the 0.3 would just kind of squeeze it or whatever. So, okay, right. What graph is this again? No. Yeah, these little things are the slope, but the actual graph I draw in there is the y graph, right? The original function. We're graphing the solution. Remember, the slope field is the solution. It's the y. These little segments are the slopes of y, yes, but they're the direction of y. So when you say this is x squared, that means y is x squared. What are these equations over here? These are y prime, right? This is y prime. So the graph over there is a parabola, but that doesn't mean the y prime is an x squared. It means the y is an x squared. So the y would be like a 2x, okay, that kind of thing. Now, what if I had 2x as one of my choices, and 4x is one of my choices, and negative 3x is one of my choices? All of those could be parabolas, right? You know, all those could be derived. So do what? Plug in some points. Plug in some actual points. Okay? Now, there's one other thing, though, that we're kind of missing here a little bit. Okay, let's look at C. We said C looked like what? An exponential. We thought it looked like an exponential, like an e to the x kind of thing. Look down your list on the left. See any e to the x's over there? So how in the world are you going to do that? Well, yeah, but plugging in points into what? I mean, plug them into all those different differential equations, and then those just give you slopes, right? I mean, you're right. You can just start plugging in some points and see how many give you that slope. But there needs to be a little different strategy here. Now, one thing I could do is I could come over to here, this list I have over here. Does this over here help you at all? An exponential oftentimes comes from this kind of a differential equation. It has a y in it. See, we've been focused on, oh, it looks like a parabola, looks like a cubic, looks like an exponential. And we've been focused on these ones where we can just do the antiderivative, right? Or do the derivative. But what about these ones right here where we don't know how to solve them, right? I mean, how do we deal with those? So what is it about, so let's look at C. What is it about C that makes me realize it would have a y in it instead of an x in it, like what B had? Let me get where we can look at both B and C. What is it about B and C where this one would have an x in its differential equation and this one would have a y in its differential equation? What's that horizontal asymptote aspect help you with? I realize that's because it's an exponential, but
like if you just have x's in the equation, you like that, like the x equaling 0 is vertical. So I mean, if you have y's, then if the y's equal 0, you're gonna have
I actually I think I agree with you. But I'm not sure. I'm not sure you're explaining it that well.
So yeah, I'm not.
You know, but I mean, let's clarify that a little bit. In other words, why, if you just had x's in it, why couldn't you have a horizontal asymptote? Horizontal asymptote, the slope would get to be 0, right? I mean, were you thinking along those lines because it levels off, or?
Like if you have y's in your equation at some point, like those y's are going to lose 0, which means you got a horizontal asymptote. But like, so obviously, like there's no situation where you just have x's where you're going to have a horizontal asymptote.
Because this won't ever be 0 for a whole stretch. Here, when y is 0, the slope is going to be 0. Well, when y is 0, well, in this case, it must be a little different because the horizontal asymptote's not at 0. But if you had a normal exponential has a horizontal asymptote down here at the x-axis, right? Well, what happens at the x-axis? Y is 0. So when y is 0, all along the x-axis, wherever, you would have this slope of 0, be horizontal. That's not going to happen here, okay? Let me just throw this next question to you and let you think about it because it's very similar to what we're talking about. It's the next one in your document, but I'm going to go ahead and just send it to you as a poll question. So you'll answer it, and remember, under quick poll, then you'll go up and submit it. Okay, so there's 2 questions here for you to actually answer. Here's a picture of a slope field, very similar to the one we were just looking at. Okay, number C. They ask you this question. The slopes depend on x, y, or both x and y, so answer that one. And then let's go ahead and match it. Which of these differential equations would have produced that slope field? See what you think. Remember, once you decide, once you're convinced you got one, go ahead and submit. The slopes depending on x, y, and x and y are really going to be the key to do a matching problem. Don't forget to submit then when you under a quick poll. After you've answered both of them. Okay, a couple more here, a couple more to finish up, get them submitted. We won't call you out. We won't show who missed
You
it or
did
not.
that one time.
All right.
Let's do it this.
The first question. The slopes here depend on x, y, or both x and y. Now, before we show the answer, this differential equation here, just so you understand what that sentence means. What do the slopes depend on? In this one, what do the slopes depend on? X. When x changes, the slopes change, right? The slopes depend on whatever x is. Y doesn't matter. When y changes, the slope's not going to change because y isn't even in the equation. So if I had the point 1, 1, or the point 1, 2, or the point 1, 3, what is the slope at those points of the y graph? What? What is it? It'll be the same, but it'll be how much? At these 3 points, what's the slope? 3. Because in these 3 points, x is 1. So the slope will be 3. So if you were to graph that, at 1, 1, you'd have a slope of 3. At 1, 2, you'd have a slope of 3. At 1, 3, you'd have a slope of 3. The slopes there depend on what x is. If x is a 1, the slope will be the same the whole time. But if I change to a new x, I get a new slope. What about this one? The slope depends on y. If x changes, doesn't matter. Now remember, we said that was an exponential. Okay, this one was an exponential. So at the point 1, 1, 1, 2, 1, 3, the slopes are going to change. What's the slope at 1, 1 going to be? Well, we don't know what k is, but let's say k is a 1. So the slope would be 1. So at 1, 1, the slope is 1. At 1, 2, right? At 1, 3, even steeper, because if we had different versions of this, they'd be even steeper, right? If we had different k values, they'd be going up even steeper and steeper. Okay? Those slopes would be different. Okay? Because the y's change. So, some of you probably think you should change your answer now, but quite a few got it. Now, why is that? Let's go back to the picture. It's easy to see on my equations over there, but why is it that the slopes depend on y? Somebody that got it right, explain that to us. Okay, do you notice how the slopes are the same? I mean, when you look at a slope field, I think from this point forward, when you're doing a matching activity, when you look at a slope field, you probably ought to look for this. You ought to look for either horizontally or vertically, the slopes stay the same. Okay, and in this case, as I go horizontally, they stay the same. And I think what you're saying is, as you go horizontally, what's changing? X or Y? As I go this way, what's changing? No, the slopes aren't. I mean, my x or my y coordinate. My x coordinate is changing. So as I go this way, my x coordinate is changing. Is the slope changing? No, so it's saying that x has no effect on the slope. So there's no x in the differential equation. It only depends on y. When I go vertically, look at this. When I go up and down, the slopes are changing. That's because y is changing. Every time I go up or down, the y changes, the slope changes. So this one depends on y. That tells me my differential equation will just have a y in it. So my choice either has to be A or C. Okay? And it turns out the right answer is this one. Now, how do we tell? How do we tell? We've decided that the slopes only depend on y, because when we go across to different x's, slope doesn't change. So it only depends on y. So which one is it? Y squared or 1/2 y? How do we tell? Well, what do you mean? Right. This is y prime, but you can't find the original because you can't do an antiderivative because it's got y in it. This is one of these down here. Like, we don't know how to solve. We can't do an antiderivative, so how do we tell which one it is? We can't do that thing we were doing with the parabola earlier where we did the derivative. That's it. You can't do that here. How do we tell? Well, come on, 7 of you got it right. Were you just guessing or what? You did what I just said not to do. And got it right. Plot points. Plot points. Do what we did here earlier when I plotted points in here. For example, go right about, let's go right here at 0, 2. Let's go right here at 0, 2. Now, do I even care about the 2? What did we already say? The difference equation only depends on y, right? So I only really need the y coordinate. So right up here at a y coordinate of 2. Okay? So let's go to this one. Let's put a 2 in for y. What do you get? 4. So what's that mean? 4. Slope is 4. So right here at y equals 2, does the slope look like it's 4? No. So let's put a 2 into this one. What do we get? 1. How about here when y is 2? Slope look like it's 1? That looks more reasonable. Okay? Here would be another reason. Go down here to y being negative 2. What do you notice? Slope's negative. Well, heck, that probably should have been the first thing we saw. What is this telling me the slopes are always going to be? Yeah, if y prime is y squared, that tells me the slopes have to always be positive. And I can tell down here the slopes are all negative. There's no way it could have been that one just because of that. So there are a variety of things you do. So when we want to do a matching thing and figure out what differential equation goes with this, there's several strategies you use. The first strategy, I think, is what's it depend on? Does it depend on just x, just y, or is it going to be both x and y? That's the first thing to look at. Once you narrow it down to that, then on this one we said, okay, it's just going to depend on y. So it's going to be one of these two. Then we got to get more detailed. So now we say, okay, let's plot some points. Let's pick some y values, see what their slope is when we plug them in, and see if that corresponds to the matching slope there. Okay, I'm going to send you another one here and see if we're getting the hang of this at all. Okay, answer this one. Oblique means diagonal. Okay, vertical, horizontal, and then oblique means diagonal. Okay, let's finish up. All right, and the answer is, oh, wonderful. Well done. Should we look? Yeah. The one person, no, don't look. Okay. Well, I guess we know now, don't we? All right. So, okay. Now, listen, think about it this way. Which one's the easiest one to solve? Differential equation. What's the only one we do know how to solve? When it depends only on x, right? When it depends only on x. Now, as far as answering this, I'm not sure you have to memorize whether it's vertical or horizontal. I'm not sure that's the big thing. I think what you want to do is picture. Excuse me. So, if it only depends on x, what that means, and here's my example right here. This would be the example. If it only depends on x, that means when x doesn't change, then the slopes don't change. Well, that's on a vertical line. If x is 1, on a vertical line, x is always 1. On this one, for example, the slopes won't change. So it says, if it only depends on x, then the slopes will be the same when x is the same, which is on a vertical line. And so the reverse of that would be if it depends on y, then the slopes will stay the same along the horizontal line. Okay? Because along a horizontal line, y is not changing. So the slopes won't be changing. Okay? All right. Now, turn your worksheet over to the back side then, where you have that matching, or maybe you're already there. And that's the next thing we're going to work on. Now, there's some of this on the second worksheet I'm going to give you today, and there's also some on tomorrow's book assignment, and guarantee on your first quiz that we take, there will be a page of the quiz that will look like this. Differential equations down the side, and a group of slope fields here, and you have to match them. Okay? So let's revisit the one we did together here, where we talked about this was 2x. Now we did it because we saw a parabola in there, and to be honest, those are the easiest ones. So probably, if I'm looking at a bunch of slope fields, I might want to do the ones that depend on x first. And so I might say, okay, the ones that depend on x would be the ones where you have a vertical line. When x doesn't change, the slopes stay the same. When you go this way, the slopes are changing, right? The lines change. And that's when x is changing, okay? So this one depends on x. And so then I might say, okay, since this one depends on x, now we might look at it and say, well, what's it look like? Well, it looks like a parabola. Well, if that's an x squared, then the derivative of that would be like a 2x or something like that, and that's where we could find it. This one we said looked like a sine. Now, isn't this one also depend on x, a? Doesn't a here depend on x? Same thing. If you go on vertical lines, when x doesn't change, on a vertical line, x doesn't change, the slopes aren't changing. So that one depends on x. So that one looks like sine. So which one is that going to match up with? Which one is a going to match up with? 3, right? Remember, this is the y graph. Looks like sine. So the y prime graph must be a cosine. Okay? Now the other thing you could do, remember sine and cosine could be shifted and stuff like that, is you could pick a point. I mean, look at b. This is when you can narrow it down as well. Look at b right here. Look at the point 0, 0. Okay? Well, when x is a 0, plug in here. What do you get? Cosine of 0 is what? Cosine of 0 is 1. Does it look like the slope is 1 there? Looks like it is. So that's another way you could tell. But you know it's got that kind of that sine cosine line. Okay, and then finally, what do the ones look like that have both x and y in them? Well, look down here towards the bottom. Look at k down here. They both change, right? On a vertical line, as x is changing, those slopes are changing. On a horizontal line, as y is changing, they're changing. I said that backwards. As y is the same, but they're changing. So this one has both x and y in it when they look like that. Okay? And so that's how you can narrow it down. Okay, let's go ahead and have a little bit of work time here to work on that, and then I'm going to pass out the other worksheet, which has some more of the matching on it, but then it's also got some where we're going to draw the slope fields, and I'll go through that with you. Okay, so you can help each other out, work with a partner if you want, or just compare answers, but go through and spend some time trying to match these. Yes.
So we talked about, you want to do that later still, or do you want to do it?
Well, what I meant by later was like Wednesday.
Wednesday? Oh.
I mean, I attempt to.
Sounds good.
My Friday will be reviewing, probably quiz next Monday or Tuesday. So, wouldn't be anything too new, I wouldn't think, by that time.